Finally, we are in a position to discuss how weighting interacts, dances a tango as you wish, with stratification. So, why would selection probabilities be different from stratum to stratum? There are two main reasons, and of course we can think sometimes of more in a given context, but two main ones also occurring in the Belgian health interview surveys. A subgroup is small, a stratum is small, yet we are scientifically interested in it. So, for example, if you're interested in making inferences about the German region, you could not simply take it proportional to its size, because that would give you, let's say, 30 or 40 or 50, 60 interviews for that region, but you may say, no, the minimum is 300 or 3,000 for that matter, and that would lead to a huge oversampling in Belgium as a whole. But while we are analyzing the data of the German region on its own, or the German community, it doesn't matter. We really want a minimal sample size in that region. We still want valid inferences at the level of the country as a whole, so then we should not pretend that the German community is 3% of the population, even though that's not much. No, it's even less than that. It's 0.6% of the population. Okay, that's one reason. Sometimes it's not because we focus on one stratum, no, it's the opposite. We focus on several strata at the same time. I'm not saying the country, no. Several strata at the same time that we want to compare. What is the difference between Flanders and Wallonia in terms of body mass index? If we present the results, we don't want to be confronted with different estimates. All right, that's going to happen, but then also two different standard errors. It makes the comparison statistically no problem, even though you will lose efficiency. That's another reason to then choose equal sample sizes. But very confusing to present to a general audience. If you say the body mass index in Flanders is 18 plus or minus 3, in Wallonia it's, for example, 22 plus or minus 1, are they now different, yes or no? Because the point estimate of Wallonia is overlapped by the Flemish one, but not the other. It's a mess. So if we can make that a bit cleaner, better, and therefore we often choose equal sample sizes. But the strata are not equal in population size. So again, if we want to make inferences about the areas as a whole, then we need to weigh. So the two reasons are a little different. In the first case, the focus is on one stratum. In the second case, explicitly on a comparison between strata. But in both cases, focus is on strata. So we use weights different from simple proportionality, or we use selection probabilities, I should say, different from simple proportionality, so that I can reach my goals. But if I still am interested at the end of the day in inferences about the population as a whole, weights need to be brought in for correction of bias. So, let's consider the following example. A certain subgroup is 10% of the population, subgroup or stratum. So we have two strata, 90% and 10% of the population. With an unweighted scheme, you would get 10% in the sample, of course, on average. Now, if we need a sample which includes 100 individuals of the subgroup, then we need a total sample of 1,000. But maybe we say, wait a minute, that's too much. We actually do not need so many people from the large stratum, we just need more people from the small stratum. So rather than inflating both strata, we inflate only one. So let's look at the table. The population is 5,000 people, 4,500 versus 500, so 90%, 10%. But the sample portion we take is only 10% in the majority group, but 20% in the minority group. So that gives us for 50 people and 100 people. The unweighted percentages would be 81.8, 18.2. But if we choose weights 1.5, and then we look at the number of individuals, but after weighting, 450 times 1 is 450, 100 times a half is 50. So the weighted numbers are back to the population numbers. The weighted percentages are correct and the inferences will be correct. What's the net benefit? we can do the calculations or we can do the math at the level of the population as if we had started with 4,500, 10% of each. But, so we're back to where we began. What's the matter now? Well, when we look at the minority group on its own, we do have 100 interviews, and that's twice more than 50, so we have more precision there. Will this whole thing lead to reduced precision? That's a tricky question. Does this now lead to reduced precision or increased precision? Generally, we say using weights decreases precision, but here we're not sure. Well, it's not an exceptional example, but the thing is, for a given total sample size, the weighted version is less precise than the unweighted version. But here we are tempted to compare a sample unweighted with 500 interviews for 50 and 50, and then weighted with 550 interviews for 50 and 100. So weights decrease precision, but of course you have a bigger overall sample size that increases precision. And what the effect is of the two together, we don't know. So if we make a comparison, don't change too many things at the same time. This is a perfectly legal way of working, but very likely you will get a little bit increased precision because you happen to have more individuals. If you say the total sample size should be 500, you can do that, and then you can take 81.8% of 500 and 18.2% of 500, and the total will be 500. The fractions will still be like 450 to 100, but then you will say, okay, I have a sample of size 500 with a reduced majority contribution and an increased minority contribution. Likely the overall precision will have decreased a little bit. That is a fact of nature. That's a fact of using weights. Okay. So, fine, we can always do that. Yeah, but if the regions, the strata, I should say in general, are geographically determined, it's usually not so difficult to do all. But that's not always the case. If you're focusing a certain ethnic group, but they're not completely living in a ghetto or so, they are merged in with other groups, but not everywhere in the country. You can, for example, select a city or a town or a neighborhood or a quarter and oversample that area. Yeah, you will have your minority group, your ethnic group. You will also have others that are oversampled. Okay, but once you have the data, you can do, again, you can do the math, and you say that in a certain group, 50% belongs to your group, whereas in the country as a whole it's only 1%. Well, oversample that area. And for every 10 people you get extra, there may be 5 from that group. So yeah, there's a little bit of a loss there, because the other 5, fine, they will be part of the survey, they don't contribute to the subgroup. But if you have to do it in the country as a whole, you would have a huge sample size before you reach an acceptable one for the minority group. So this area approach works really well. Okay, good. Let's look at the artificial population and give an example. So we stratify 1, 2, 3, 4 or 1, 4, 2, 3, and then you select samples proportional to stratum size. 1 out of 2 units, for example, 1 and 1. No weighting needed because you have 2 strata of 2 people, you select 1 out of 2, same selection probability. And now we take a third stratification, 1 versus 2, 3, 4. Now you take a sample, 1 from the first stratum, that's going to be 1 of course, and then 1 from the second stratum could be 2 or 3 or 4. So unit 1, a selection probability 1. Units 2, 3, and 4 have selection probabilities 1/3. Okay. So, what is now the probability of selecting certain samples? In the first stratification, let's just take that one with 1, 2, and then 3, 4. 1, 2, and 3, 4 cannot occur. But the others can occur with probability 1/4. We have something different in the second stratification, but similar. And now, even though we have the same overall sample size, and we take samples of size 2, 1 per stratum, there are only 3 samples possible. That's pretty obvious, but so this really depends on the partitioning. Now, you see that typically samples that are somewhat on the larger end do not occur. So I'm a little bit worried about bias. So the corresponding estimators. If I calculate, for example, the average of the numbers 8, 10, 10 and 12, it's equal to 10. If I calculate the average of simple random sampling, and that's still the benchmark, 6, 8, 10, 10, 12, 14, the average is 10. But now magically also here, the average is 10. 7 plus 10 plus 13 divided by 3 is 10. But what I don't understand is nowhere else did the numbers 7 and 13 come up. So how can 7 be related to the average of 1 and 2? The average of 1 and 2 is 1.5. 1.5 times a fractional number is, I don't understand it. So how do we do the estimation? Well, this is of course how you calculate the average with one small correction here. The 1/4 in the final calculation should be 1/3, of course. Now, the reason why it works is we calculate not an estimator in the unweighted sense, in the classical sense, it's a weighted estimator. So sample 1, 2 produces, look at that, very, very important message. Sample 1, 2 creates a value 6 in simple random sampling with the second stratification, but produces a value 7 there. So the same sample can lead to different estimators. This is a very important point for every statistician and methodological person. Having a data set alone does not allow you, does not enable you to properly analyze it. Why? You need to know not only the data, you need to know what was the design behind the selection, the capture of the data from the population. And because here we sample with differential selection probabilities, we will take that into account and we will apply a different estimator, producing not a sample average, but a weighted sample average. So, for example, in the first case, we divide every number by its inverse selection probability, so by the way. We have 1 divided by 1, 2 divided by 1/3, so 2 multiplied by 3. 1 plus 3, that's, or 1 times 3 times 2, that's equal to 7. We multiply by 4, that's the population size, of course, overall. And then we divide by the sum of the weights. 1 over 1 is 1, 1 over 1/3 is 3, 1 plus 3 is 4, 4 cancels with 4, 1 plus 6, 7. Okay. The variances for simple random sampling without, with, and stratification. Well, 6.67 without, 10 with. We know that without stratification is more efficient. And then we have 2 for the first stratification, 6 for the second stratification, so it has gone up. It's not so dramatic, but it has gone up. The second stratification actually is even worse, but that's because it was deliberately chosen, the second stratification here, to be a poor one. We remove heterogeneous samples, we retain homogeneous samples. That's a recipe for high variability. So generally, weights, the use of weights does decrease precision, but there is no rule, no law saying that it's less than or equal to, so it's always going to happen. No, in some cases you can do clever weighting and you can do really stupid unweighted stratification, and that's because you defined your strata very poorly. That could be, of course, worse. Given the strata, if you don't change the strata and you sample weighted rather than unweighted, you usually get less precise results with weights. But you should not change too many things in the equation at the same time. Okay. Now, that concludes how stratification intervenes with stratification. In the next section, we will look at weighting and multi-state sampling and clustering.